Hello, everyone. Good morning, good afternoon, good evening to all, depending on where you're joining us from today. We're here to discuss the topic of mechanical recycling and the role that compatibilizers play in recycling plastics. Plastics find use across a wide range of products, from packaging and consumer electronics to building and construction materials, because they're lightweight, durable, and inexpensive. Over the years, the increased use of plastics in products has led to an environmental problem stemming from the improper disposal of plastics waste. And across the world, consumers, brand owner companies, regulatory bodies are trying to tackle this problem through various approaches. One such approach involves mechanical recycling, in which post-consumer plastics waste is collected, sorted, and shredded and processed into flakes for use in plastics. Mechanical recycling is really the dominant technology today and offers an economically viable option for reusing plastics, but it faces challenges, whether stemming from the variability and contamination of the plastics waste stream itself. In today's series of talks, we'll hear from leading experts on how they're developing compatibilizers to address these issues and advance the field of mechanical recycling. Before we get started, a quick note on the On24 platform. You can resize the presentation and video windows by clicking and dragging them, depending on what you want to focus on. On the lower side of your screen, you'll have the option to access helpful and relevant resources. And finally, feel free to submit your questions for the speakers to the Q&A box. We'll take all questions at the end of presentations. Our first contribution today comes from Dr. Scott Trenner, Principal Scientist at Milliken & Company. Dr. Scott has over 20 years of experience in R&D in the plastics industry. His experience includes discovery, development, commercialization of novel polymers, polymer additives, technology scouting, acquisition, and licensing. Since joining Milliken & Company in 2008, he has led the development and commercialization of novel additives, polyolefins, and he co-invented and commercialized Delta Max performance modifiers, which enables recycled PP in durable goods. He's currently the global technology lead for Milliken's plastics additive sustainability efforts, driving R&D efforts in sustainably enabling technologies, and serves on several working committees and advisory boards for associations ranging from Alliance to End Plastic Waste, Association of Plastics Recyclers, and Plastics Recyclers Europe. With that, over to you, Scott.
Thank you, and thanks for the introduction, and thank you to TA Waters for inviting me to take part of this. So what I'd really like to do, and I'm happy to kick this off, is kind of give a very high-level introduction to where contamination comes from, kind of how to deal with it, how it's currently dealt with, and hopefully lead or begin the discussion that Professor Ellison and Robert Bearlocker can kind of dive into a little bit deeper. So as was mentioned, I'm Scott Trenner. I'm at Milliken & Company. This shot that you're seeing here is our headquarters. It probably looks a little bit like that this morning since it's in the morning. And I am coming from you right behind that magnolia tree right there. So for those of you who are not familiar with Milliken, we're a privately held manufacturing company founded in 1865 in Maine. We're owned by the fifth and sixth generation of the Milliken family. And we've been recognized for many years in terms of innovation, leadership, and manufacturing excellence. We have 4 operating divisions. So our textile division makes everything from apparel, industrial uniforms like firefighters' uniforms, automotive reinforcement tapes like the ones shown here in this picture. And, in terms of recycled materials, they're a large user of recycled PET fiber, specifically in our Polartec lines of fleece. We have a floor covering business. So we've been inkjet printing and producing carpeting for over 50 years now. And they're quite a large user of recycled polyamides. We have a healthcare division that makes wound dressings, compression bandages. And then I sit in our chemical division where we have a couple of different businesses. We produce specialty silicones for the semiconductor industry, colorants and ingredients for detergents and consumer products. And then I'm in our plastics additives division where we focus mostly on additives for polyolefins that help improve processability, including reducing the amount of energy it takes to process, toughness of recycled polypropylene, clarity, and other aesthetics. So when we talk about sustainability, it's really a team effort that requires really everyone in the supply chain and even consumer input to make this work. So I just kind of wanted to briefly touch upon some of the collaborations that we're part of in terms of pushing sustainability of plastics and really all materials available. So, we're in global organizations like the Alliance to End Plastic Waste, maybe more regionally in North America with the Recycling Partnership that really pushes education of the consumer to better recycle at home, which really cleans up the recycling stream and reduces contamination. And then some of our other partners are listed here. So when we think about advancing plastic recycling and mechanical recycling and all the advanced recycling techniques that we're hearing so much about these days, I think it's really nice to kind of take a step back and try to figure out where all of these different processes fit in. So I have a slide here that we pulled from a paper that I published a couple of years ago, kind of giving the linear supply chain that we see at the top row here. Hopefully you can see my pointers, where we go from feedstock extraction and production, monomer production, plastics production, part reduction, and then use. And it's really the post-use that we're talking about, or that we'd like to improve upon as we move forward. And the first step in that is mechanical recycling. And I'll show an example of what that general process looks like on the next slide and why it's so important for us to not just reuse these materials and recycle these materials, but really utilize mechanical recycling as much as we can, because really has a tremendous impact in reduction of energy use and also global warming compared to using virgin or new materials. The next loop, and I'm using a polymer loop to describe this. So this is termination started by the Ellen MacArthur Foundation, is purification, and I'll touch on that a little bit at the end and where that plays a role in terms of reduction of contamination. And it's really just kind of a extension, I would say, of mechanical recycling, where in this polymer loop, you're not really degrading the material. You're trying not to degrade the material. So the plastics are all staying in the polymer chain. You're not trying to degrade or go back to monomer. The next loop we'll touch upon is the depolymerization. And this is really focused on PETs and polyamides, where the materials are broken down into their base monomers that are reused to enter the plastic production, which are then made to use parts. And then finally, you have the conversion technologies in the molecular loop. And that's mostly focused on polyolefins, where these materials are broken down either by gasification or pyrolysis or by some of the new emerging technologies in this space into petrochemicals and syngas, which really start all the way back at the feedstock production. And as we go from right to left in this, trying to make a material or use a process and stay in the highest possible value that you can, going from right to left, you require higher stream. So if you're going back into food contact applications, for example, mechanical recycling is an option, at least here in the United States. There's some regulatory issues in Europe that prevent it for some of these materials, especially polyolefins, but you really need a very pure stream, and contamination can play a significant role in restricting some of these uses. So as you continue to the left and you go to purification, depolymerization, and conversion, ideally the required stream purity decreases, so you can account for more contamination and a broader range of contamination, but they all still have their restrictions in terms of throughput and what the contamination could do to any catalysts that are in part of the process. So that's good that you can use a dirtier stream or more contaminated stream. The counter to that is, as you go to these molecular loops and monomer loops compared to mechanical recycling, the energy input is significantly higher. So what does the mechanical recycling process look like? It's relatively simple. So once you put something into your curbside bin, it goes to a MRF. That MRF separates those materials, and we'll see an example of their product in the next slide. And then those bales of recycled plastics go to a recycler or a reclaimer. And in the first process, you can kind of see the little jugs and jars coming through here, and you have some folks that inspect that material. It then goes, that then gets washed and chopped into smaller parts, and it goes through a sink float tank, which is really important in reducing contamination, and I'll touch on that on the next slide also. Those polymer shards or chunks are then dried and then put into an extruder. The extruder then melts the materials, and then pelletizes into a form that can be used directly to make another product, whether that be a car bumper, another soda bottle, if it's a PET stream. One thing that this doesn't show well is, you have multicolors going in, and here you have individual colors going out. In reality, that doesn't actually happen because all the colors kind of get muted, so you tend to get something that's gray or black as an end product. And again, the reason we're focusing on this, and the reason this is really important for all of us as we strive to get our net zero goals and reduce carbon footprint, is shown here in this publication of or summary of an LCA done by the Association of Plastics Recyclers. And what they're showing is the percent reduction in each one of these factors for recycled materials versus or recycled plastics versus virgin plastic production. So if we go from the left to right, we have PET, high density polyethylene, and polypropylene. So if we look at total energy that goes into making a pellet from virgin PET compared to recycled PET, the recycled PET uses about 80% less energy. The polyolefins are about 85 to 90%. And then if we look at global warming potential, so CO2 emissions or CO2 equivalent emissions, the recycled materials are between 70 and 80%, 70, 75% lower greenhouse gas emissions. So as we think about recycle streams and designing packages, what we really want to do is keep as much of this material in this mechanical recycling loop to really get the most benefit from an environmental perspective. So I touched upon bales, and I thought it'd be really important to kind of touch and mention where some of this contamination looks like. So you put things into your recycle bin, a truck or something picks them up, it goes to a MRF, so a materials reclamation facility. They sort typically by infrared sortation and maybe also manually, depending on how new your MRF is. And then they produce what's called a bale. So this is a bale of polypropylene. And while I can't tell you exactly what the contamination is in there, but I'm pretty sure there's probably something other than polypropylene in there. So that's one source of contamination. A second source is in the materials that are used in individual packaging. So this is a really nice summary by Reigard and de Mister in Europe, where they took different packaging formats. So from left to right, PET bottles and trays, polyethylene, polypropylene bottles and trays, expanded polystyrene, and then different films, and deconstructed the materials and kind of averaged out the materials of construction. So if we start with the PET, we could see that, the PET soda bottle or water bottle in this case is about 80% PET, and then a bunch of other materials. So, there's a little more drink left in there. But what I wanted to point out is this 7 to 8%, that's the cap. And similar with trays, that's a polyolefin. And similar with the PET trays, it's mostly PET, but then you also have some amount of polyolefin lidding. And that's where that sink float process and the recycling process becomes really important. So PET having a density greater than 1 sinks, polyolefins having a density less than 1 float. So it's a really efficient way to remove some of the contamination during the recycling process. Now, when we get into polyolefin packaging, like PET bottles, polypropylene bottles, and polypropylene trays, you can see that the majority of those materials are what they say they are, right? So the PE bottles is 77% polyethylene in this case, but it has about 10% of that polypropylene as a cap. And since both of them have densities less than 1, they both float, so they're really difficult to separate in that sink float sortation. And that's where some of these new emerging technologies and sortation technologies like flake sorting are coming into play. So, after the material is in a bale, it gets chopped into the flakes, right, that go into that sink float separation. After sink float, you could put that through a second IR sorter, which sorts by flakes. And in that process, you can get to 97, 98% purity. So, for this polyethylene bottle, you'd get a stream that is 97, 98% polyethylene, and then the little bit of polypropylene. For the polypropylene packages, it'd be the other way around. You get 97, 98% polypropylene, a little bit of polyethylene. Where sink float and flake sortation tend to fall apart is in film recycling. right? So if you look at a multi-layer film or monolayer film, it's not so important because the vast majority of that is whatever that monomaterial is, so polyethylene in this case, and the residual 10% will typically get removed in the wash. But then as you get into multi-layer films, here's where it becomes much more complex. So in this case, we have something on the order of 55%, 56% polyethylene, and then there are other materials such as EVOH, PET, polyamides, which all have a really important function in terms of protecting the contents of that. I think I have an example here. So this is a very simplified example of a multi-layer film where you'd have polyethylene on the outside, polyamides for toughness and also barrier performance, EVOH for oxygen barrier. And, unlike the larger multi-material packages where the individual materials can be sorted by either sink float or by flake sortation, these are all kind of stuck together. And I think Professor Ellison here in a few minutes will talk to you about this PET polyethylene film and work that they're doing to compatibilize those materials. So before we move on into changing designs and what we or Milliken are doing in helping to reduce contamination or overcome it, I thought it'd be fun to go through a quick little experiment and thought process as to, so we have contamination. When do you measure for it and how do you measure for it? So if we look at that polypropylene bale, and here's the Association of Plastics Recyclers bale spec, they say that bale, and sorry for the inches, so it should be 30 inches, so a little less than 1 meter by 1.5 meters by about 2 meters in dimension. Should have a density of 15 to 20 pounds per cubic feet. So if I am trying to understand contamination of this material, we use TADSCs all the time to measure contamination, but how do you get a representative sample? So if I look at that bale, it's about 350 to 450 kilograms of material. That's 70 million potential DSC samples, and you could almost guarantee that each one of those are going to be a little bit different, right? So say I go through a sink float process and maybe even flake sorting and process that into a Gaylord of material, right? So a Gaylord is 650 kilograms. That's 130 million potential DSC samples. Now you've gone through a bunch of processing and some melt mixing, so maybe samples will be more representative, but it's still difficult to understand where that contamination is, how much it is in there, and how consistent that sample is. And then finally, maybe you measure it on the final process. So you take this polypropylene recycling, you make it into a car bumper. Car bumper is lighter in weight than each one of these other samples, but you're still at 2.7 million potential DSC samples. And really, if you needed a compatibilizer, because that's what the DSC sample said, it's really too late at this point. So as we think about the supply chain and the different processing that a recycled material goes into, we really need to think about where we measure contamination, where the contamination enters, how we can reduce it most importantly, and then how we can overcome it finally. So what are we doing in industry? What is Milliken doing? So I mentioned earlier and showed in their slides that we're members of the Association of Plastics Recyclers here in the United States, Recyclass in Europe. And one thing that they're trying to do is they're putting together and harmonizing guidelines on recyclability and how to reduce contamination in the package before it even gets to the consumer. So I've gotten 2 screenshots here for examples. So the one on the left is APR's guidelines for recycled rigid packaging. And one thing I'll point out, and it's probably almost impossible to see on the slide, but this top one right here is about the dispensers or a pump dispenser on like a bottle of lotion. And what they're suggesting is that that material is not made out of polyethylene. It's made out of something like PET or a polyamide or something that has a higher density than one so that it's separated, more easily separated in that sink float process. The other example here is Recyclass. So it's their guidelines for polyethylene packaging, and it goes and tells you, what the main material of that construction should be. And in here it says that it should be mostly polyethylene, which makes sense for polyethylene flexible packaging. And then lower down here for the more advanced packaging that requires some barrier, right? So it says no more than 5% EVOH. Again, trying to reduce that dissimilar material that's difficult to remove or almost impossible to remove during the recycling process. So where Milliken plays a role in this in helping our customers and brands reduce the amount of dissimilar materials in packaging. One example is with our UltraGuard family of materials. So this is for HDPE multi-layer packaging, and it's a bit of a complex slide, but what I have here on the left is a example of a multi-layer package. It has about 10 layers in this case, all of which have their specific utilization. And what I want to point out here in the middle is what we're trying to do is keep that EVOH dissimilar material below, at or below that 5% that RESI class or APR suggests. And what I have published here is some water vapor or oxygen transport rate, right? So that really dictates the shelf life of whatever's contained in that package. And if we look at this example film, it has a WVTR of 1.86 grams of water per mil thickness of film per meter square per day, and an oxygen transport rate of just under 1 cubic centimeter of oxygen per meter square of film per day. So this is something that might be, that is really kind of a very generic package that for maybe crackers or something like that. So what we're doing is if you take and add our UltraGuard into 3 of these layers, so into the core layer and the print web, and then the subskin layers and the barrier web, we can decrease both the water vapor transport and the oxygen transport and really upgrade the performance of that film while still maintaining that 5% EVOH layer. So now we can hit a more demanding application like pet food, for instance. And then if we take our UltraGuard and add that into a couple of different layers, so again, the core layer, now the laminating skin, and in addition to the subskins, we can reduce that water vapor transport again and oxygen transport rate again, and really get into much more demanding applications like chip bags, for instance, and more greasy foods that are both water, very water sensitive. You know, you don't want soggy chips, or require high oxygen barrier performance. The next application I'll touch on is the Deltamax family of additives that was mentioned in the introduction that I helped develop and commercialize. And this family of additives really helps overcome some contamination, mostly from maybe polyethylene in the polypropylene recycling stream. And this is a case study that we worked with a customer on, and they wanted to injection mold this this storage slash seat for a garden or garage. And our customer is having problems in processing these materials because some of the contamination. We developed a solution that had 1 weight percent of our Deltamax 8200 added to their recycle stream. And the result was they were able to increase the amount of recycled material from 40% to 90%. So again, more recycled material, increasing the demand for recycled material, I think, which is really important to this, to the recycling supply chain, but then also making a product that performs with a much lower greenhouse gas footprint. They were able to also reduce the processing temperature and reduce the cycle time, which also has some energy savings and productivity savings. And the way that additive works is it better disperses some of the contamination or some of the dissimilar materials. So this is an example. This is an SEM micrograph, not necessarily of that bench, but of a polypropylene impact copolymer. And you can see here these little divots and bumps. So that's the rubber phase or the contamination you can imagine it as. So a 30 micron scale bar here at the bottom. And then if that's the base composition, if you add our Deltamax additive to this, you can see that the non-miscible phase is much smaller, much more better dispersed, which leads to better processing. And then finally, the third example I want is some of the collaborations that we're doing outside of the walls of Milliken. So this is an example of a startup that we're supporting, Pure Cycle Technologies. They're developing a purification process that, or they're scaling a purification process that was developed at Procter & Gamble. And for those of you who do polymer chemistry in the lab, right, it's very similar to how you would purify something in the lab, a little more complex. You essentially just take the polypropylene in this material, you dissolve it, you filter, and you reprecipitate it. So the example that I have on this slide is from carpet. So this is where they've taken a post-consumer carpet stream, they've ground it and consolidated it into this kind of plastic polypropylene pellets that you see here. They run it through their purification process, which removes most, if not all, of the contamination. And then we were able to develop these and injection mold these deli cups here that you see here. And while not quite as good as mechanical recycling from an environmental perspective, it's still much better than virgin production and much better than pyrolysis, where their LCA is showing that they have a 35% reduction in greenhouse gas emission equivalents compared to virgin polypropylene, and an 80% reduction almost in energy compared to virgin polypropylene. So with that, thank you so much for your time today. I'm really looking forward to discussion later on. And I believe I will hand it off to Professor Ellison to move us on to his section.
All right, thank you. Thank you very much, Scott. You set me up nicely. In fact, I may go through some of our intro slides relatively quickly. Am I good to just start, Bharat?
Yeah, just a quick introduction. So Professor Ellison is the Zsolt Rumi Innovation Chair at the Department of Chemical Engineering at the University of Minnesota. He earned his BS in Chemical Engineering from Iowa State University and PhD in Chemical Engineering from Northwestern. And from 2008 to 2016, he was a faculty member at the Department of Chemical Engineering at the University of Texas, Austin, where he was also affiliated with the Material Science Engineering program. Prior to joining that, he was a senior scientist at Roman Haas company. And currently his group works on the structure, dynamics, and processing of micro nanostructured polymers, engineering sustainable materials. He's received numerous awards, including the National Science Foundation's Career Award, DuPont Young Professor Award, and many more. So over to you, Professor Ellison.
All right, thank you very much. So very happy to have the opportunity to talk about a little bit of our work today. This work is focused on multi-block copolymers as compatibilizers for PET and PE mixed waste streams. And I really want you to look at this as perhaps a tutorial, maybe a model perhaps of how you might develop new compatibilizers for new waste streams. I also want to thank TA Waters for the opportunity to present. It looks like there's great attendance today, so that's really good to see. This work was sponsored by the Center for Sustainable Polymers, which is a National Science Foundation Center for Chemical Innovation, headquartered at the University of Minnesota. The work is primarily the thesis of a graduate student who just defended her thesis, Xiaoyu Peng, also with important contributions from Kei Nomura, who was a I-Prime industrial fellow visiting us at Minnesota for 2 years. And then Professor Kevin Miller at Murray State University also helped in the synthesis of some of these molecules. So I'll go quickly through this introduction because really Scott set up the challenge nicely. We're focusing on polyethylene terephthalate and polyethylene. In aggregate, those two materials represent a significant portion of the market. They're oftentimes used in concert and in food packaging in particular because PET is a good gas barrier material and polyethylene, PE is a very good moisture barrier. Of course, these materials can be sorted and recycled, particularly if they are in forms where they're relatively pure, for the bottles as one example. But there are multi-component products that are essentially not recycled at all, and Scott mentioned this in terms of food packaging. It's not uncommon to see in food packaging many layers. Here I'm just showing 3 for simplicity of understanding why we're doing what we're doing, but totally acknowledge that many of the packages are far more complex. Oftentimes in these systems, you have a PE for a good moisture barrier, PET for a gas barrier, and then there oftentimes be a tie layer or adhesive between sometimes polyurethane or malleated polyolefin. And I think what I'm going to argue to you today is that those tie layers could be repurposed or at least designed with the intention of thinking about them as also promoting recycling later as compatibilizers. Polymer laminates or food packages are a major form of waste. This here is a study from 2017, the International Coastal Cleanup, where they collected plastic items that washed up on beaches. And the top three aren't too surprising: cigarette butts, plastic beverage bottles, and the caps. But number four is food wrappers, which are exactly these kinds of multi-component materials that are difficult, if not impossible, to separate the layers. And so dealing with compatibilizers that might be able to handle those would be good. Of course, these compatibilizers are also useful in cases where you might have contaminated waste streams. So the idea here is that, and I can't quite see the top of my slide for some reason, but the idea here with compatibilizers, just to lay everything out very generally, is that polymers in mixed form are 95% of the time immiscible. And this means when you try to melt reprocess them as they're in their mixed state, they phase separate. And they phase separate into domains that are typically a few microns. Because they're immiscible, they have relatively sharp interfaces, which means they're weak because they don't have entanglements across the two components. And so the mechanical properties are usually very poor. If a crack starts across this material, it reaches these weak interfaces and it faces essentially little barrier to propagating further. And these materials are brittle and often cracks run through them quite easily. The idea is that polymeric compatibilizer, and today I'm going to talk about a block copolymer, which is a copolymer-like surfactant that can localize at the interface between these two miscible polymers. It decreases interfacial tension, which helps you refine or reduce the disperse phase or minority domain. And ultimately, that molecule stitched across the interface also improves interfacial adhesion. This can also suppress domain coarsening upon processing, which makes these materials much more stable from sort of a property perspective. Ultimately, this produces robust mechanical properties and tough blends if the molecules are designed appropriately. So we have been interested at Minnesota in multi-block copolymers for some time. Actually, this work I'm going to talk about today was inspired by work that came out of the Coates, LaPointe, Bates, and McCosco group. They had really focused on polyolefin mixtures, which is another critical mixed waste stream. These polyolefin mixtures are difficult to separate for all the reasons that Scott highlighted. And in this work, they developed some multi-block copolymers of polyethylene and isotactic polypropylene that could be used in polyethylene and polypropylene blends to stabilize them and render them with robust mechanical properties. And so they looked at a number of different additives. I'll just highlight these tetra blocks here at 5% or 1%. This shows in this stress strain tensile test that the properties of these blends with isotactic polypropylene and polyethylene with 1% of the additive produce mechanical properties that are in between the two pure components. And so this is a signature of compatibilization. It's a signature that you produce a tough blend given the strains are at break or in excess of 400%. You can compare and contrast this to simpler molecules. You might argue this diblock copolymer in green is a simpler molecule, but at 1 weight percent, it's not effective. I didn't point this out, but I'll just note that the blends that don't contain any compatibilizer are shown kind of in the middle panel here as an inset. And those materials fail or have a strain at break of something like 10%. So even though both components are very ductile, tough materials, when you place them in a blend, it's these weak interfaces that really dominate. And they proposed a lot of mechanistic detail on how they think this happens. The idea is that these compatibilizers can reach across the interfacial width to reach into the pure components. They can engage in entanglements into those pure homopolymers if they're long enough. And ultimately, if they're long enough, they can also co-crystallize with the pure components. And these are mechanisms of providing strength or stress transfer across those interfaces. So we began thinking about other important blend systems. As I mentioned, polyethylene and polyethylene terephthalate is one we were thinking a lot about. And we immediately began thinking about ways in which you might design a compatibilizer that serves dual purpose. Could it serve as an adhesion agent in the use of that package? But then ultimately in a melt reprocessing case where you'd be recycling the system, perhaps it could also serve as a compatibilizer, rendering these blends tough. So let's first talk a little bit about how these were synthesized, because these hadn't been made before, and the synthesis is a little bit challenging because, as you can imagine, PET and PE are not miscible in a lot of common solvents. So the way in which we made these was to make two dihydroxy block precursors. Here I'm showing dihydroxy PET. It's about 4,600 grams per mole. We make the PE blocks separately. In this case, we're using ring opening metathesis polymerization followed by catalytic hydrogenation. These two components can then be coupled together using a diacid chloride, which installs linkages and units that look exactly like the PET precursor. And ultimately, we can make these materials with on average, something like 10 to 15 blocks, 45,000 grams per mole. We designed these in this way because we were really focused on trying to get entanglements and also make the blocks long enough that they could reach through and beyond this interfacial region to potentially co-crystallize. And in this case, this is why we chose these of roughly 3 or 4 kilogram per mole. And you can see what the entanglement molecular weights are below there. So that is a system that the block precursors can actually join together in kind of a random fashion. So there's a chance that you could have blocks of the same type joined together sequentially. We also wanted to make a alternating system, and the way in which we did this is to make the diacid chloride of PET such that the only reaction that was really dominant was that those diacid chlorides react with the dihydroxy PE. And in this case, you end up producing a system that you would expect would be essentially alternating. Roughly the same total molecular weight and blocks per chain. And so we call this the alternating sequence. We made a control tri-block, again, using some of the same methods. The main difference in the tri-block here is it has 15,000 gram per mole blocks, 3 of them. And so the total molecular weight is roughly the same as the multi-blocks. But we had to make the monohydroxy PE by a different method. This is by polymerization of anionic polymerization of butadiene, again, followed by catalytic hydrogenation. The characterization of these materials is a little bit tricky, and I'm not going to spend a lot of time on this, but I'll just point out that due to the way in which these are coupled together with a step growth like chemistry, the number of possible N groups are several. And so NMR analysis looking at N groups has to account for all of the possibilities. This is laid out very nicely in one of our papers. And the NMRs have to be run for fairly long. So some of these NMRs we run for 24 hours to collect enough signal to noise. We also do size exclusion chromatography. This is typically done for us in a high temp SEC. The high temp SEC uses a TCB mobile phase, and we use a trick for chromatography where we first dissolve these multi-block copolymers in TCE and then inject them into the TCB mobile phase. And qualitatively, we can tell that in conjunction with NMR, that the PET precursor has been essentially consumed and that the N groups of that PET precursor are few. And then the SEC tells us that there isn't a lot of PET precursor left in the system. So I won't spend a lot of time on the characterization because there's a lot of detail to putting all the pieces together here. We also use a differential scanning calorimetry, a TA differential scanning calorimetry, in fact, to measure the melting transitions of the system. These indicate that we have relatively pure domains of PE and PET. And in all of the cases, whether it's random, alternating, or the controlled tri-block. And you can see a summary table here, but I've mentioned most of these details throughout. So in order to study how these materials compatibilize what would be an analogous mixed waste stream, we chose a PET LLDPE mixed waste. It's 80% PET, 20% LLDPE. And we add sequentially, or essentially actually all together, with the block copolymer we're evaluating from 0.2 to 2 weight percent. These blends, of course, are pre-dried. That's very important for polyesters. We make films of them. We quench those films. In the state in which we quench these films, the PET is only lightly crystalline, while the PE is more crystalline. And we cut a dumbbell for tensile testing. So these are tensile tests for these blends with different compatibilizers. The stress strain from a typical tensile test. You can see PET homopolymer there has a strain at break at something like 300%. When you make an 80-20 blend, that strain at break goes down significantly, something like 10% or even less. However, with these compatibilizers, whether it's multi-block random or multi-block alternating, both with 4K blocks at 2%, the strain at break is at least as good as PET, if not better. And the tri-block copolymer, surprisingly to us, was also quite good. Now, I'm not showing you the polyethylene homopolymer component here because its strain at break is, I think, about 1,000%. But just know that exceeding the PET homopolymer is an indicator you've effectively compatibilized. So this is just a summary of the things that I've already said. Of course, this is just at 2 weight percent, and we'd like to explore using as little as possible. The compatibilizers are expected to be more expensive than the components that they're used with. And so we did a study where we looked at just the strain at break as kind of a surrogate for the toughness of the system as a function of concentration of the additive. Again, you see the neat system has a relatively low strain at break. If you look at either the random or alternating multi-block copolymer, they're effective at something like 0.2 weight percent. And I guess in this system here, we haven't gone much lower. But 0.2 is so low that it's actually a little bit difficult to load them into the compounder with confidence of the amount that you've put in. So going much lower than that is going to require us to do larger batches. The tri-block copolymer wasn't as effective, and so this we see that you need roughly 1 weight percent to get to a point where the tri-block is competitive. But clearly, all 3 block copolymers over 1 weight percent achieve a comparable strain at break to neat PET, shown by that dashed line. And so there's something about the compatibilization efficiency of the tri-block copolymer. It's not quite as efficient. We have a hypothesis as to why this is. We think it might be more prone to forming micelles, but need to do more work there. Of course, the toughness that is exhibited in these blends by the action of the compatibilizer, we think all of the same mechanisms are likely operative that I talked about in PE IPP, including entanglements across the interface and also co-crystallization. So we need to do a little bit more work here. These are now just hypotheses, but clearly the multi-blocks are efficient and effective. You can see the stress transfer across the interface just by doing a cryofracture, where you can see the dispersed phase and the minority domain of PE deforming in systems where there is expected to be block copolymer at the interface. However, the neat blend shown in the upper left, you can clearly see the gaps. And in many cases, you can see the dispersed phase simply just fall out of the PET matrix without compatibilizers. So this is a good indication that the mechanism is the localization of those at the interface. To probe this a little bit more deeply, we've done some peel tests to look at how these materials peel apart. And so we make laminates where we take the block copolymer and place it at the interface, and then peel these systems apart to test their peel strength. The block copolymer layer is about 220 nanometers, so it's relatively thin, and we produce that by spin coating. And then the peel test is done simply by doing a 90-degree peel test with an Instron. So in the adhesion of these cases, these are tri-layer films with this adhesive block-copolymer inner layer. Again, all three block-copolymers perform quite well. They'd be competitive with many existing tie-layer materials that you see in industry for PE and PET. Tri-block copolymer perhaps is a little bit lower, but multi-block copolymers seem to perform the same regardless of architecture. We also wanted to understand the migration of these materials, thinking about preloading them perhaps into films that would be made into multi-layer film. So we actually took these materials, compatibilizers, and preloaded them into polyethylene, and then adjoined it to a PET film and basically annealed that stack for some period of time. So we're really probing the migration of the compatibilizer to the interface here. We look at that as a function of time, and of course, again, we're using a peel test as a way to test adhesion. And for the random 4K, you see this ramp up, of course, where the material has to diffuse or transport to the interface. It doesn't quite reach the coverage that it does when we make these tri-layer laminates. So the peel strength isn't quite as high. It's not so surprising. The alternating 4K looks somewhat similar to the random, but the tri-block copolymer really struggles to get to the interface. And we think this has a lot to do with its propensity to form micelles in the polyethylene domain, which are intrinsically larger objects and transport more slowly to the interface. And so this is something that we're still investigating, but clearly the migration of that particular compatibilizer is slower. So I hope I've just given you a sense for the kinds of experiments and interpretations that we have in designing compatibilizers for PE and PET. These compatibilizers are new, first time they've been synthesized. They're incredibly efficient. We're still understanding how that's true at 0.2 weight % or even lower. And the tri-block copolymer is less efficient. We think this is due to slow migration and possible micelle formation. Finally, I'll just remind you, this was part of the NSF Center for Sustainable Polymers, and we have a number of metrics by which we try to understand how we're having impact on sustainability. Here I'm showing just a few of those categories, which I won't dwell on. And then finally, to be a little bit self-serving, I'd like to mention that the CSP and my group specifically have numerous postdoc positions available. If you're so inclined to perform research in this area, please reach out. Thank you.
All right, thank you, Professor Ellison. Our final talk for the session will come from Dr. Robert Sherman, the Technical Director of the Special Additives Division at Barlocker, USA. Before coming to Barlocker, Robert held several R&D positions related to polymer additives and stabilization in different resins. This included acrylics at Adastec Acrylics, polyethylene at LyondellBasell, polyesters at GE Plastics. He received his PhD in chemistry from Oklahoma State University. He did postdoctoral research at Texas A&M and has a BS and MS in chemistry from Southern Illinois University. He's currently the chairman and board of directors for SPE's Polymer Modified Additives Division. Over to you, Robert.
All right. Thank you very much for the introduction, and definitely thank you for inviting me to be a speaker. So today, my talk is going to be focusing on the whole concept of stabilization of post-consumer and post-industrial recycle, specifically for trying to improve the overall properties and try to preserve the resin the way it should be. So, overview, I'll be discussing quickly who Barlocker is, talking quickly on the basics of stabilization and recycling, discussing our T-blend stabilizer, which is what we usually offer to recyclers for stabilization, and giving a few examples. So Barlocker is a company. We are a German-based company based out of Munich, been around for 199 years. We're a manufacturer of basically two classes of things: oleochemicals, specifically looking at things like metal soaps like calcium and zinc stearate, which are lubricants and antacids used in the polymer industry, as well as additive blends. And when you combine those two concepts together, you can see that we're quickly become a global leader when it comes to PVC stabilization. We're also very well known for other polymer stabilizations like polyolefins, styrenics, etc. Like I said, we are a global company. As you can see from the map, we're all throughout the main regions of the world, and we tend to supply regionally, but we always have our sister companies there to back us up. I'm based out of the bottom bear in North America, which is our Cincinnati R&D and manufacturing headquarters. And like I said, we are globally known as a PVC additive company. I come from the non-PVC side of the company, which is called specialty additives. This is where we manufacture the metal soaps like calcium stearate, zinc stearate, magnesium, etc. And we use those in a variety of applications, such as non-polymer applications, which can be quite interesting, lubricant blends, which can be used for making things like wood plastic composites, as well as stabilizer blends, which could be custom or off-the-shelf type materials. This includes our RST and T-blend technologies. And these are applied to a variety of things, including recycling, which, like many other companies, we are members of APR, and we focus heavily on recycling. And even this year, Bearlocker is going to be having a sustainability summit here in Cincinnati, where we're bringing together brand owners, resin manufacturers, recyclers, equipment manufacturers for a 3-day, basically, get-together to discuss recycling and how we can help one another. Because basically you can't do recycling by yourself. And if you need more information about this, you can find it on my LinkedIn page or Bearlocker's LinkedIn page. So when it comes to stabilization and recycling, this is just a very high-level overview, just to get everyone on the same page here. But again, of course, this is only talking about mechanical, not chemical. And this is not really focusing on either post-industrial or post-consumer. Both of them often fall under the same issues when it comes to contamination and degradation of antioxidants. But when it comes to mechanical recycling, what we see out there is recycling, downcycling, and upcycling. Of course, recycling is trying to take and make something of equal value, such as taking a milk jug and turning it back into a milk jug, which is actually quite difficult to do. Downcycling, where you're taking and making something of lower value or end of life, like, for example, taking a milk jug and turning it into lawn edging. That's fairly easy to do because you definitely don't necessarily need additives to do that because it's lower quality. And then finally, upcycling. That's when you're trying to make something of higher value, such as taking a milk jug again, and now you're turning it into like high-density pipe, which has a 50-year shelf life, which is actually fairly easy to do with the use of functional additives and stabilizers. And so a lot of what we're focusing on here at Bearlocker in the US, Europe, and throughout other parts of the world, especially now, is focusing on recycling, trying to actually make things back into what they originally were. So I've been doing recycling for Bearlocker for about 7 years now, and we do a lot of work with our customers where they send us materials. And we see a lot of things when it comes to both PCR and PIR, which overlap. Number one, the resins are usually very poorly stabilized. And two, the materials are often contaminated, sometimes very heavily contaminated. And unfortunately, a lot of these contaminants are also pro-degradants for the stabilization packages, which are found inside the resins, which are put in there by the original resin manufacturer. And so some of this contamination can include things like dirt, the former contents of the package like food residues or mold. The wash water detergent can actually be very detrimental to the additive package. Incompatible resins like PVC, even trace amounts, basically tear through pretty much every other polymer. The age of the resin, when you're doing multi-pass extrusion working at a resin manufacturer, you do all 5 of your passes in a 2-hour period of time. When you're dealing with post-consumer, post-industrial, you have no idea how many years those resins have been around and allowed to decompose in the oxygen and sunlight. Also, very poor quality resin, even poor quality virgin resin, unfortunately. And of course, multi-layer packaging, which we just kind of heard about. And so what are the effects? Of course, color is number one. It's hard to find a very white, clear post-consumer product. Usually they're highly colored. Odor is, of course, a big issue, especially when you're dealing with detergents. You have loss of mechanical properties, especially in polypropylene. Gels, when it comes to film, which can actually render films unusable. Reduced lifetimes for the product. Inconsistent parts and processes, so you need an engineer to run each production line, as well as an inability to use your own regrind or recycle, which I've seen in several instances. So
Dr.
when it comes
Robert,
to yes,
looks like your video dropped off. Maybe you could just check, see if it's on.
Oh.
Sorry about the interruption.
That's odd. There we go. Perfect.
Thanks.
Thank you. Yep. So when it comes to stabilization of polyolefins, it's very complicated. You're dealing with a variety of processes, most of which are based on free radical chemistries, as well as basically the resins exposed to oxygen. Oxygen and free radicals pretty much love to tear up the polymer. This can be caused by exposure to sunlight, heat, as well as actually running multipass or running extrusion. So this is part of the problem we have to deal with as a stabilization company, trying to stop all these fun free radical chemistries from occurring. And so when you look at, this is a slide I stole from my German colleague, but basically when you're comparing virgin polymers to recycled polymers, there's a lot of stuff in there that's not found in the virgin. Specifically when you look at, for example, carbonyl groups, acidic groups, double bonds, the difference between virgin and recycled material can be a couple orders of magnitude in difference between the two. And, that basically is what's resulting in all this color, odor, mechanical degradation, et cetera. Along with that, there's also a lot of metal impurities. A typical resin coming out of a resin manufacturer has almost no metal impurities. Most of that's going to be from the catalyst. But when it comes to recycle, you're dragging all kinds of new metals in from the extrusion process, the wash water, former contents, et cetera. And all of those act as oxidation catalysts and help destroy the overall antioxidant package that's present. And so these are the sort of things that we have to overcome. And again, this is something you don't normally see when you're working at a resin manufacturer. And this is what delineates a resin manufacturer from recycling. There's a huge difference between what you're doing in a lab and what's actually happening in reality. So when it comes to stabilization, basically there are three main components to the stabilization package. And this is what every major resin manufacturer out there is using when it comes to polyolefins. You have antacids, you have a secondary AO and a primary AO. These three materials act together as one protecting the other. So you have the first line of defense, which is your antacid. These are going to be things like calcium or zinc stearate or zinc oxide. So strong antacids, which are going to destroy your catalyst residues, because the catalyst residues otherwise will destroy your antioxidants. Your second line of defense is going to be your secondary antioxidant. They are there to basically give you melt stability. These are going to be phosphites, typically, things like 168. And their job is essentially to protect the primary antioxidant and get it through the melt process. Finally, you have the primary AO. These are typically going to be phenolics like 1010 or 1076. These give the product long-term stability. And basically almost every resin that you can find on the market is going to have all three of these materials present. However, a lot of these materials have already been depleted during the resin manufacturing step, as well as any subsequent forming of the part, as well as shelf life. And so when we do recycle, a lot of times we find that it is a good idea to go ahead and add more of these additives back in, typically adding all three back in to give a nice, well-rounded stabilization package. So our typical answer is based on our RST technology. RST is a very strong antacid that also acts in many instances like a stabilizer. However, a lot of times recyclers don't have the capabilities of adding multiple additives. So our answer is our T-blend technology. T-blend, basically the T standing for 3 components. So it contains all 3 of those components. You have your antacid from the RST, you have a secondary AO, like say 168, and a primary AO, so your phenolic, like a 1010. So you have all 3 together, able to act together to basically restabilize the resin, since most of the time the AO's already been depleted. These are put together in a simple 1-pack so that people can easily dose this with just a single feeder. And we have a variety of them. And typically we work with customers to find out which one works best with their product as well as their process. So this is just an example showing melt stability doing multi-pass extrusion. On the left, you can see the effect of having no stabilizer present. This was a problem with a customer who was having issues with gel formation. And of course, as you do multi-pass, you can see that even under extremely mild conditions, there was basically your melt flow is dropping, and this is creating gels. Addition of just a small amount of stabilizer, 0.3% of any of these T-blends, 1111, 1214, 6111, at 3,000 parts per million, gives you complete and total stability through all 7 passes, which then results in reduced gels. One other test we often do is an actual measurement, a rough estimation of how much active AO you have. This is OIT, or oxidation induction time. This is a simple DSC experiment where you heat a sample up to 200 degrees C under nitrogen, switch to pure oxygen, and you wait to see how long it takes before the resin starts to decompose. The longer the wait, the more active AO that's present. This can only be applied head-to-head type comparisons. You can't compare polyethylene and polypropylene, but within the same resin, it works quite well. This customer was having issues with processability, and you can see that it starts out with a very nice OIT for the neat unstabilized resin, but as you do, even on the first pass, you're down to 11 minutes. So there's basically no AO present. And as you continue, you have no AO present by the time you get to the 5th pass. In this case, we just added 0.15, so 1,500 parts per million of stabilizer. And both of these gave very, very good overall stability and solved the problems. So the next thing I have is a very short case study, which I'm still working on. Basically, this has to do with extrusion blow molding. We went out, acquired some high-density PCR, stabilized it, and then we took this material along with virgin up to Beckham and did a variety of blow molding trials, which I'll then present in a few months at SPE's blow molding conference this fall. But basically, when you look at part of the problems that people are facing right now, using PCR and blow molding can be very limited due to PCR quality. It varies, just like we discussed earlier. Bales vary from spot to spot, and then of course the same thing applies to the individual pellets. And so this can cause people to basically chase their parison whenever they're trying to do blow molding. And the whole idea here is if you can stabilize the resin properly, maybe you don't have to do that so much. And so we basically were trying to determine the influence of stabilization on blow molding grade PCR. We have 2 products that we're looking at, which is just pure homopolymer high-density PCR. So these are like milk jug resins that are actual post-consumer. And we also took some of the exact same material and compounded it with 3,000 parts per million of our Varipol T1111. Both of these saw the exact same heat history. We then were also able to acquire some virgin homopolymer resin from a resin manufacturer. And so we were able to compare all 3 of those resins along with 50-50 blends. And we did initial work by doing extrusion multi-pass under very mild conditions, basically to mimic blow molding conditions. So starting out with looking at the influence on melt flow. The first thing we have here is the virgin material on the left. As you can see, starts out at the correct melt flow and then is slowly dropping off as you go through multiple passes, showing that there are some issues with overall stability. As we then go to the PCR, we can see the PCR actually is much lower. So a lot of these changes in rheology were caused when the resin was originally compounded. Addition of stabilizer to the PCR, the middle set, shows very stable rheology. Actually, it's up where it's supposed to be, around that 0.75 area, so that it has actually been protected as it was doing its initial compounding. And then looking at 50-50 blends, this is why we have to do a lot of work with customers. You would think that virgin plus PCR would be halfway in between. In this case, it actually wasn't. It was actually much lower because we're probably consuming all the AO from the virgin. But the virgin stabilized PCR was actually perfectly in between, as you would expect. As you then look at oxidation induction time, won't go too much into this, but you can quickly see that you can easily tell if the resin's been stabilized or not. Both of the sets of samples that had AO in it show huge improvements in oxidation induction time, indicating that there is active stabilizer. Maybe this is a little bit too much, but as a first pass through, it gets us in the ballpark telling us that stabilization is giving an effect. However, the PCR itself is definitely dropping off, and the virgin with PCR did show an even bigger drop off. When it comes to color, of course, the virgin is virgin, so it's going to be very nice and white. It was a very nice, pristine white pellet, as you'd expect. And then when you start doing combinations of PCR, anything that contained stabilized PCR did show improved whiteness compared to the virgin / unstabilized PCR product. And the exact same thing can be seen for yellowness index. Virgin, of course, has much better color, and anything with stabilized PCR showed an improvement in color. And then one last bit of data I have here actually has to do with parallel plate rheology. So this is complex viscosity. This is in my opinion, a better way of looking at rheology than, say, your standard melt index or melt flow, because you're looking at a variety of frequencies. In this case, we're going from high angular frequency on the far right to low frequency on the left. Very important on the far left for low frequency, because you have, this is going to tell you more about your parison as it hangs, and you want it to be not changing, shall we say. This was all done at 200 degrees C under constant strain. And basically what we're showing here, you have virgin with, let's see if I can do a pointer. We have virgin with polyolefin, which is the green line with the red dot, which is down here at the very bottom. This is where we want to be. This is what virgin material at pass zero should look like. As you then look at the other materials, specifically the pass fives, you can see that the PCR containing materials or virgin materials are all moving up higher. So you have a material that's thicker. It's got cross-linking in it, and so it's not going to act exactly the same way. And as you look down through the list of materials here, basically everything that has a different colored center has some AO in the PCR, and each of these do tend to match much more closely to the virgin pass zero than the non-stabilized. But the most important thing that we see here is you look at the virgin AO PCR 50-50 blend, it perfectly falls on top of the virgin pass zero. So from this information, we should be able to actually match up what we expect from blow molding data. And when we look at the blow molding data, that's what we see. The virgin material, we dialed in the blow molder based on virgin material, and then we were trying to do basically drop-in type data. So going from virgin to PCR 100%, you see that there's a huge change in bottle weight. This is because the parison is different, because there's different rheology. As you then go to the AL with PCR, 50-50 blend, it gets better. Virgin with PCR that's been non-stabilized is even better because you have that virgin material in there. And finally, the best one of all compared to the virgin is the virgin that contains stabilized PCR. So you end up with something that much more matches the virgin. And if you go back and compare the order that you see here to the order that everything lines up here, we're actually able to use parallel plate rheometry to guesstimate the results that we're getting from blow molding studies. So this basically allows us to take PCR, virgin material, stabilization, and then correlate the lab results to real world results. And eventually we'll have all the full data associated with this trial, and that'll come out later this year. But basically, in conclusion, when it comes to PCR, it's a continuing problem here in the U.S. that as we try to keep up with it and try to keep materials basically as close to virgin as possible, additives, compatibilizers, and a variety of other materials can help us to do this, along with all, of course, the engineering solutions from like melt filtration, et cetera. And so basically, if anyone has any questions, you can always contact me or contact Bearlocker. So thank you.
All right, thanks everyone. That was an excellent series of talks that really touched on the challenges and issues that we face with mechanical recycling today, and really connecting how compatibilizers can advance this, can get properties of these recycled resins as close to virgin as possible, which is what converters are looking for, especially in terms of drop-in replacements. We've had a series of questions come in. We encourage you to enter your questions in the Q&A box if you haven't done so already. Of the questions that came in, there were a few themes that emerged, and I'll try to touch on some of those. Maybe we could get started with that. One of the first questions that I'd like to start off with is around the OIT results that Dr. Sherman showed in your presentation. The question was around, does OIT really correlate with heat aging in an oven? Is it necessarily quicker, and can it really be reliable at the same time? So maybe you could comment on that.
So comparing multi-pass extrusion to heat aging, you mean?
Right, just in terms of comparing different materials and getting confidence that OIT can be a suitable replacement for oven aging.
Well, yeah, a lot of times you will do the same tests together. So you will age, for example, tensile bars in an oven, and you will, of course, on a regular basis, pull tensile bars, measure tensile, look at color, look at surface defects, et cetera, and then also correlate that with OIT as you're going through the testing. At least that's the sort of work I would do back in my previous positions at resin manufacturers. It does do a good job of trending, though.
Great, thank you. This question is a little bit more broad-based, and I'll direct this to Dr. Trenner to start off with, and then Professor Ellison and Dr. Sherman, if you take a shot at it. This is around paper contamination in plastics waste and cellulose derivatives, right? As we know, you have labels, you have other materials that come through that bale when it comes to the recycler. How does that impact the properties of the processed recycled plastic, and what solutions are able to tackle that issue?
Yeah, so that's a difficult problem, and especially if you look at, here in the U.S., and I think Robert touched on it too, right? Polyethylene milk jugs is a really important recycle stream, and most milk jugs have paper labels. So the way that's dealt with, and it's not ideal, is after grinding during the washing process, the adhesives that are used are typically water soluble or water removable. So the paper label and adhesive ideally is removed cleanly from the surface of the polyethylene. And then that gets removed during the filtration of the wash fluid. If it continues to persevere, I guess, beyond the wash, inline melt filters can remove paper. If it gets through that, and for those of you that aren't familiar with that process, so that's basically the filtering of the melt down to about 20 to 30 microns, depending on what kind of filter you have. And then after that, it just kind of makes its way through into the final product. But if you look at what APR and Recyclass have done recently, they're really moving on to a push to move away from paper labels for that exact reason.
Yeah, I would just add, I think Scott covered the paper label aspect nicely. I would just add that many labels are polymeric with print on them. And so in that case, given that they're polymeric, they may just be able to be incorporated into the waste stream and not cause such a problem. But.
Right. And I definitely agree with what Scott says. A lot of this, whether it's cellulose from labels or paper or even splinters from pallets, typically people are using your classic ARIMA, NGR, Stirlinger sort of melt process to help filter out any of this impurities.
So our next question is really around additives and how they can be removed. So one of the attendees, they were trying to work with recycled HDPE. They dissolved it and sent it through a glass filter. But they still ended up with the dyes that was present in the original product. And clearly we know, we've looked at some examples where adding these additives can help to improve the brightness. But when you start with something that has colorant in it, how do you go about tackling that issue? Dr. Scott, do you want to get us started off with that?
Yeah, so from a purely mechanical perspective, it's very difficult, if not impossible to do, right? There are some emerging technologies in the wash where they neutralize colors or agglomerate them to remove, and those are, trying to remember the recycling company that's scaling those. It might be ARIMA. And when you look at purification type of recycling processes like PureCycle that I mentioned, or APK or polystyrene, typically, they'll dissolve the material, they will filter, and then they'll reprecipitate. And during that reprecipitation process, in an ideal world, the inks and pigments stay in solution and the polymer is able to be filtered off and removed.
Dr. Sherman, anything to add there?
Yeah, from a pure mechanical recycling, it's almost impossible. I don't really actually know of any process other than adding lots of pigment on top of it and getting the color you want, as long as it's not white.
All right. Our next question is for Professor Ellison, and this is really around the multi-block copolymers. The question is around, does the ideal block number and length, does that depend on the blend ratio? Does it depend on the homopolymer molecular weight or branching structure? And how can you go about predicting that?
Yeah, I think that's an excellent question. That's some of the work that we're pursuing presently. It's going to be dependent on the system. What are the chi parameters between the two homopolymers you're examining? And in reality, the mixtures are even, as we've heard today, more complex than just two components. It's just two components are very nice for fundamental studies, understanding connections between molecular architecture and their performance. So I guess my short answer is I don't think that information is really well known, and that's still an active area of research. It's not even clear, to be honest, that 10 or 15 blocks, like I showed you in the work that we've done, is necessary. Maybe it's only 4 or 5, but that's an ongoing area of inquiry. If you want to learn more about the perspective we have on multi-blocks, we did just publish a paper in JAX AU that kind of covers an overview of those kinds of compatibilizers that might help you understand more about the area.
That's great. And then a couple of sort of follow-up questions related to that. Around the NMR solvent and parameters, if you could share any information around that, and also how did you go about accurately measuring the molecular weight of the multi-block copolymers Was it using SEC or some other techniques?
Yeah, so the NMR was done with deuterated tetrachloroethane at elevated temperature. You can find that information in the supporting information of our ACS applied materials. I think it's 2020. It's in the supporting information of how we did all that characterization. The SEC of those materials, the precursors, before you connect the blocks together, can be done nicely with high temp SEC for the polyolefin and with HFIP SEC for the polyester. And those can be done with Waters instruments, many other instruments with light scattering detection, and you can do that absolutely. The multi-blocks are a little bit more challenging because you have two components which are present at roughly 50% each, and they're not soluble in many common solvents. And so SEC is not that useful for the multi-block, which is why we lean hard on the NMR to do a careful N-group analysis. Of course, there's a distribution in those materials because we couple them by way of traditional sort of step growth type coupling reactions. And so the total chain lengths have a distribution as well. So I hope that answers. There's no one silver bullet in characterization there. You kind of have to piece together a number of different techniques to develop the picture.
Right. That's helpful context, especially as you touched on some of the challenges there with SEC for these materials. The next question really touches on a slide that Dr. Sherman showed towards the end, and this is around the data with the multiple passes of the recycled resin. The question is specifically around, shouldn't melt index get higher with multiple passes as the viscosity and molecular weight decreases? And I think you maybe touched on this briefly as you spoke about the rheology data that followed. So,
right. So in this case, these were all done with polyethylene. So polyethylene is going to cross-link, so the molecular weight goes up, so the melt index will go down. Polypropylene will do the absolute opposite. It'll go through chain scission, and so the melt flow will go up. Good question.
And that kind of just leads us into our next question is around, how much does chain scission really affect, and the drop in molecular weight affect the blending and the reuse of plastics? And is there a way to tackle that using compatibilizers? Dr. Sherman, maybe you get started, and then Professor Ellison, if you chime in on that.
Sure. Yeah. So whether it's chain scission or cross-linking, all of these processes are quite detrimental for polyethylene or polypropylene when you're looking at trying to use them in post-consumer or post-industrial recycle. Trying to preserve that, basically the identity of the molecule that you made in the reactor, is extremely important. Otherwise, for polyethylene, you're going to get gels. For the example I showed with blow molding, your Pearson's going to change, so you're going to get total weight changes in your parts. For polypropylene, you're going to get a lot of chain scission, so your melt flow goes up, and mechanicals, of course, drop off very rapidly. So stabilization is extremely important because you want to maintain that exact molecule that Dow and Exxon and Lyondell spent minutes making. So.
Yeah, I think I would just add one of the things I learned from Robert's presentation that I guess I hadn't fully appreciated is that even though you may add compatibilizer molecules that help make mechanical recycling products more useful, it's important that you also think about the additive packages that must go in addition to those compatibilizer molecules. To the extent that those additives are consumed or depleted, either in use or in the recycling process, you really need to replenish them so they serve their purpose. So that's what I would add.
Dr. Trenner, would you want to add to those comments?
I think that summarizes it well. I think as we continue to move towards a more circular economy and the recycling of packaging over and over again, we need to do everything we can to keep that initial molecular weight as high as we can to keep those mechanical properties. I think Robert's presentation showed exactly why you need to do that and reasonable methods as to how to maintain the properties of the that the producers originally designed.
This one's relatively interesting. I think it goes to one of the core challenges around recycling. And the person's asking is if it's possible to deal with LDPE that is either contaminated with the LLDPE or HDPE through compatibilizers alone, or is separation of these different grades of PE, is that even an option? Professor Ellison, if you want to get started on this.
Yeah, this is a very important issue. Polyolefins, even though they're all carbon and hydrogen, you might guess, well, they're miscible in one another, and it turns out they're not, even across grades of polyethylene. It's an issue. So yes, I think in cases where the polyolefins, whether it's polypropylene and polyethylene or different grades of polyethylene, compatibilizers could be sufficiently designed to work in those systems. I think as Scott pointed out, the polyolefins are typically very difficult to separate into pure forms. And so you oftentimes have some amount of contaminant of other polyolefins in the ones that you'd like to have completely pure. So yeah, I think compatibilizers could be a viable strategy. I'm not aware of polyethylene compatibilizers, but it's certainly something that could be done.
Dr. Trenner?
Yeah, I'll agree with Professor Ellison. I mean, I think especially in the linear low density separations, those are going to be very difficult with any process that exists today. Maybe I think the high density versus the lower densities, you might be able to do that with, there's some magnetic type separation processes that are being scaled in Europe, and also some eddy current type sortation processes that are being scaled by, I can't remember the name of the company, but they're out of the UK, where you can make finer separations via densities, different densities. So maybe if you're at like a 0.95 or higher high density, you can separate that from a 0.9 low density or linear low. But separating the linear and linear lows are going to be continuously challenging.
Yep, and I definitely agree as well. It's going to be very difficult. Ideally, you don't mix them together in the first place, like whenever you're making your structure. But then again, a mixture of polyethylenes isn't that bad. When you start mixing polypropylene in with polyethylene, now you get your phase separation and immiscibility and mechanicals and rheology just go crazy on you. So to me, blending polyethylenes isn't so bad. It's more when you get into the other, specifically polypropylene mixed with any of the polyethylenes, that you get problems.
Right. I think that's an ongoing challenge in sourcing these types of recycled materials from the waste streams that are available today. Our next question kind of follows up on that. Multi-layer films, right? So when you have EVOH in with polyethylene, they're asking if it's possible to use water vapor transmission rates to detect the remaining amount of EVOH in the final recycled material.
So yes, but I don't know that it's necessarily. So I would suggest using FTIR or DSC in that. I mean, in order to measure WVTR, right, you're going to have to produce some sort of article or a film that you're going to test, and that's time consuming, and I would say most recyclers and even don't have that capability. I think EVOH, if you can get as I mentioned, a representative sample of your recycled material, it's pretty easy to measure via FTIR or DSC.
And I would add the water vapor transmission rate will be dependent on the structure and how the EVOH is positioned relative to the film surface, so on and so forth.
If it's just a dispersed phase, you're not going to measure any difference in EVOH. Most likely it has to be a continuous phase for it to have a significant difference in water or oxygen transmission.
Yep, I agree 100% with what they said.
This next question talks about measuring the interfacial tension after you've added compatibilizer and asking about the best method to be able to do that. Clearly, adding a compatibilizer lowers the interfacial tension. How would you go about measuring that? Professor Ellison, maybe you want to get us started?
Yeah, I mean, people have used spinning drop tensiometers. They have used pendant drop type methods. I guess the question would be, what would you use that measurement for? What would the outcome be? And in the end, at least for us, we feel that mechanical properties are sort of where the rubber meets the road. You can infer that material has made it to interfaces by simply looking at the dispersed phase as mixed, and then after some amount of static thermal annealing. And you're looking for smaller dispersed phases in systems which contain compatibilizers compared to without. And then those systems will generally, if the compatibilizer is at the interface and of sufficient molecular weight to stabilize the system, this dispersed phase will remain small. It will not coarsen with time. So those kinds of tests we use frequently to infer interfacial activity. And obviously coupled then with mechanical properties, you have a good indication you have a good compatibilizer.
We'll close on with one final question around substances of concern and the recovered material being used for food contact applications. How can you qualify that there's no substance of concern, and can you grade it for use in food contact applications? So Dr. Sherman, maybe you should share your thoughts on that.
Sure. Yeah, I mean, there's a variety of technologies out there where basically people are allowed, here in the US, are able to get to basically a letter of no objection when it comes to their resin for subsequent food contact use. I know that a lot of the people that are doing that have to go through very rigorous testing, including like spiking the resin with some of these substances just to prove that there are no pesticides, for example, in the final product. So I know there's a lot of rigorous testing, and then I'm just going to guess that you're just going to have continuous testing as well to ensure that none of this is getting back into the resin.
Dr. Trenner?
Yeah, so, I mean, just to add to that, if you look at the food contact regulations, at least in the States and in Europe, what one of the requirements is control of your source material. So the kind of base assumption is if the majority of your material, and by majority, we're talking 95, 98%, comes from food contact applications, then those substance of concern should not have been in the original article, right? So there's a little bit of a leap of faith there. Otherwise, you're measuring for thousands of different molecules via gas or liquid or some other type of chromatography. The newer regulations in Europe coming on that will determine whether a inventive or a new process is acceptable for food contact. I think they essentially require you to test every batch, which is 20,000 kgs or something like that, for a battery of different substances to see if they're in there or not. I think as we talk about more contaminated streams than the food contact post-consumer type stream, you're going to have to go to the more advanced recycling, whether that be purification or depolymerization or the deconstruction, to really to be sure that those substances of concerns aren't in your final product.
All right. So with that, I want to thank Dr. Trenner, Professor Ellison, and Dr. Sherman again for your time and the wonderful presentations today, and the lively discussion that we've had afterwards. A recorded version of this panel discussion will be available through the TA Instruments website and can be viewed at a later time. We look forward to seeing you again in a future panel discussion series touching on different topics within the area of sustainability polymers. Thanks, everyone. Have a great day.
Thank you.
Thank you.